Hi everybody. Today we're going to start talking about work and power. So our objectives for this lesson are to define the terms work and power, and then to see how we can solve some problems about work and power. So first, let's define work. If you apply a force to an object, and the object moves or changes its position as a result of that force has done work on the object. So there's three key requirements to knowing whether or not work has been done on an object. You have to have a force applied to it. The object has to change its position or have some displacement. And that force must be the cause of that displacement. So there's a cause and effect relationship there. You can have a force exerted on an object that doesn't displace it, which means it doesn't do work on the object. So how do we calculate work? Work is represented by an uppercase W as its variable letter. And in order to determine how much work is done on an object, we multiply the size of the force by the displacement the force causes. And then sometimes we're going to multiply that by the cosine of the angle that's between the force and the displacement. Most of the problems that we look at, the force is going to cause the displacement parallel or in the same direction as the force, which means the angle between the force and the displacement is 0. And if you remember, the cosine of 0 degrees is 1. So that would simplify our equation to work equals force times displacement. The reason that we have to include that cosine of the angle between force and displacement sometimes is because sometimes our forces are not exerted in the parallel direction to the displacement of the object. Sometimes, if you remember when we were looking at forces being applied at an angle, only a component of our force is what is changing the motion or causing the displacement of the object. And in those cases, that's when we're going to have to know the angle in between the force and the displacement. But most of the time, we're just going to say that work equals force times displacement. The unit of work is a joule. It's represented by an uppercase J. And it is a derived unit that is defined as 1 Newton times a meter. So it's a Newton meter. Now there are a lot of good examples of work that we see in our everyday life. Some of them that you think are work may not be work in the science sense. You may think you do an awful lot of work as you sit and think about how you solve your physics problems, but from a physics perspective, you're not doing work. You actually have to have a force and you have to have a displacement. So let's look at a couple of examples where we do have work being done. If we have a horse pulling a plow through a field, the horse is pulling the plow, so it's exerting a force. The plow is changing its position, being displaced in the field as a result of that force, so you have work being done. If you have a person pushing a grocery cart down the grocery store aisle, you have the person exerting a force, a push. You have the grocery cart changing its position, it's being displaced. It is being displaced because of that force, so you have work being done. And not all of our problems are going to be horizontal. We're going to have some vertical ones too. So if you're thinking about a weightlifter lifting the barbell above his head, he is exerting a force, this time in the vertical direction. He's lifting, but that's still a push or a pull. And he's displacing or changing the position of the barbell as a result of that force. So work is being done. The types of problems that we're going to look at are going to generally fall into those two categories. We're going to have work being done horizontally on an object in order to change its speed. So if we exert a force, of course we accelerate it. And if we accelerate it, it changes its velocity and then therefore changes its speed if we're working in just one direction. The other type of work we're going to look at is when we do work against another force, and that force is going to be gravity. That's when we're talking about lifting things. So let's look at a couple of examples real quick. Here we have a tugboat pulling a ship with a force through the harbor, and the ship moves 3 kilometers, and we want to know how much work is being done. First, we have to ask ourselves, is work being done? Is there a force exerted on the ship? And is it being displaced because of that force? And yes, we can say that. If that tugboat did not pull that ship, it would not have moved the way it did. So as a result, we know that work is being done. So in order to figure out the amount of work, we would do our work is equal to our force times our displacement. Now we have to think about whether or not the force and displacement are parallel or in the same direction. So we know whether or not we have to have a cosine of an angle term in there. And if we look at it, all the motion and the force are on the water. So as a result, we say that they're in the same direction. The tugboat's pulling in a certain direction. The ship is moving in that direction. So as a result, the force and the displacement are parallel. The angle between them is 0. So we end up with a simplified equation for work where we can just say work equals force times displacement. So the size of our force is 5,000 newtons. Our displacement is 3 kilometers. And now if you remember, we're going to want to express our work in joules, which is a newton times a meter. So we have to do a little conversion here to make sure that our displacement is in meters. There are 1,000 meters in every kilometer, so our displacement is actually 3,000 meters. So now we substitute. Our work is equal to our force multiplied by our displacement. And that's going to give us a total of 15 million Newton times a meter. Remember, Newton times a meter is a joule. Okay, let's look at a problem where we actually change the position vertically. We lift something. So here we have a weightlifter that lifts a set of weights, a vertical distance of 2 meters, and we want to know the work done on the weights. Well, again, we have to ask ourselves, is there actually work being done? Is there a force being exerted? Well, yes. The weightlifter is exerting a force that pushes the weights upwards. Is there a displacement? Yes, they move upwards 2 meters. Is that motion a result of the force being exerted? Yes. So there must be work being done. So again, we will have work equals our force times our displacement, and look at it and see if the force and the displacement are parallel. Yes, they're both in the same vertical direction. So our cosine of our angle is 1 because we have 0 degrees. They're parallel, so we can use that simplified equation. And now we have to think about what is our force. Well, when we lift things, the force that we're actually exerting is the weight of the object because we're working against gravity. And remember, gravity, the force due to gravity, we say the size of that is the weight of the object. So that's the force that we're exerting. So we have to go out and calculate that first. So that equals our 200 kilograms, because remember, this is a mass, multiplied by our acceleration due to gravity of 9.8 meters per second squared. And we would say the weight of that barbell set is 1,960 newtons. That's the force that we're exerting in this case when we're lifting. So our work then is going to equal our 1,960 newtons. We displace it 2 meters. So as a result, the amount of work done is 3,920 Newton times a meter, which is a joule. Right, now that we have work down, let's look and see what power is. Power is simply the rate at which work is done, how fast you do the work. So power, and it's represented with an uppercase letter P, is simply equal to the amount of work you do in joules divided by the time it takes to do the work in seconds. The unit of power is called a watt. Again, it's another derived unit, and that is equal to 1 joule per second. When we look and compare objects as to whether or not they are more powerful than each other, we say an object is more powerful than another if it can do more work in the same amount of time, or if it can do the same amount of work in less time. So let's look at some comparisons for that. Say, for example, we have our same lifting of the barbells that we just had in the previous example. So we still have 200 kilogram barbells. So they're still lifted 2 meters off the ground. But we have 2 different carnival sideshow men lifting the barbells. And we want to know which one does more work and which one is more powerful. So we have Atlas and Hercules. Each of them lift the same set of weights, but they do it in different times. So first of all, which man does more work? Well, they do the same amount of work because they both lift the same weight, so they exert the same force over the same distance, the 2 meters. So as a result, they do the same amount of work as our example previous to this. They both do that work equals the 3,920 joules. All right, so as a result, both of them do it, so neither does more work, it's the same. Now, if we ask ourselves which one is more powerful, we have to look at the amount of time that they do that work in. So let's look at Atlas. Power that Atlas exerts is going to equal the work that he does divided by the time it takes him to do it. So we'll take the 3,920 joules divided by the 2 seconds it takes him to lift it, and he does 1,960 watts of work. Right, now let's look at Hercules. Hercules, he does the same amount of work, but in a greater amount of time. So let's look, he still does the 3,920 joules of work, but it takes him 5 seconds. So as a result, he only exerts 784 watts of power. So as a result, out of this, we can say that Atlas is more powerful, simply because he did the same amount of work in less time. When we look at power, we really have to look at that ratio to see who is more powerful, or which force is more powerful, to know if it does the same amount of work in less time, it's more powerful, or if it can do more work when compared to another object in the same amount of time, it's more powerful.